Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera student. This time, in this video, we will proceed our lecture with a Jacobian function. Jacobian is a determinant of a system consisting of multiple functions which is depending on n variables. So that is the idea of Jacobian. So remember Jacobian, remember the determinant. So we have learned on how to find the determinant in matrix chapter. So once you deal with a system, which consists of multiple function, equation and so on, you will be dealing with a determinant, with a matrix. A system will create a matrix, right? So the idea is you will be having or you'll be dealing with few functions. Let's say here you have function f1, f2 until fn. So we have n numbers of function, and each of these function, until fn, is depending on n variable. So here f1 is depending on x1, x2 until variable xn. Alright, same goes to f2 until fn. So this will create a system. So Jacobian, or we denote as J, is the determinant of all the functions. So that is the idea. Jacobian is the determinant of all functions. So when I write these two straight line symbol, it means determinant. So determinant, right? Determinant of the function. So let us look at the formula of the Jacobian. So this is the formula for the Jacobian for the system of equation. Alright, so there are two here that you can choose to in order to calculate the determinant of the system. Alright, so you can find the Jacobian like this or like this. So what is the difference between the first one here and the second one here? Alright, so you know that you have a system which is f1 equal to f1 depending on function x1, x2 until xn, right? And then you have the second function which is f2 depending on x1, x2 until xn, and it will continue until you have function fn with fn depending on x1, x2 until xn, right? So the first one here, you get this formula when you treat your column here. You treat the column for f1. So you arrange the first column for f1, the second column for f2 until the last column will be your fn. And then you will partially differentiate your function here and here and here with respect to all of the variables. So the first row here you differentiate partially with respect to x1. The second row here you partially differentiate with respect to x2 until the last one here you partially differentiate your f1 with respect to n. Alright, understand? While the second formula here, that formula is formulated based on when you rearrange your formula or your function to be, okay, the first row here is your f1, the second row here is your f2 until the last row here is your fn. Okay, so the row will be for your function, and then you will partially differentiate your variable, which is by column x1 column 1, x2 for column 2 until xn for the last column. So you fix your f1, f2, f3 by row. Okay, and then you partially differentiate with respect to x1, you put in element a11. Okay, so it will be here. And then you differentiate your f1 with respect to the second variable, which is x2, and put it here. And then do for x3 until your xn. Okay, once you're done with your first function, proceed to the second function and partially differentiate with respect to x1, put it here, partially differentiate f2 with respect to x2, put it here until xn, and you will continue until the last function that you have. Okay, so you see the difference between these two? The first one, you treated your function in column. Okay, so column 1 for f1 function first, differentiate partially with respect to x, put it here. Okay, and then partially differentiate with respect to the second, put it at the bottom. Okay, and continue until the last one. Then proceed to f2. Okay, and partially differentiate with respect to your variables, okay, and put it in a column. Okay, so column at the bottom, at the bottom, at the bottom until the last. Okay, while the second formula here, you will treat or you will put your function in row. Okay, and partially differentiate with respect to each of the variables in column. Okay, in row. Okay, so the first variable, the second variable until the last variable. Done with f1, proceed to f2 and until f3. Okay, so regardless of which one of the formula you use to find the Jacobian, it's fine. You will towards the end you will get a similar answer. Okay, so it's okay, it's fine. Alright. Because it will depends on the arrangement of your system, so doesn't matter. Okay, because it is stated in the properties of your of finding determinant. Even though you change the first and the second row, okay, when you swap the position, you still will get the same Jacobian. Okay, you will still get same determinant. Okay, that is the property of the determinant in matrices. Okay. Okay, now let us proceed to the example. So given that you have u equal to exponent of negative 2x times with sines 2x and v is equal to exponent 2x times with cos 2x, then you need to determine the Jacobian for the system of equation. So in general, we can say that we need to find the determinant of this system. Okay, so first I will arrange my function to be this, so that it's easy for me to see. Alright, you have second function exponent to x cos to y. Alright, so in order to find the Jacobian for this system, I will treat my first column for u, function u, first function, and the second column I will do for my second function, which is v. So the order is the first column I will perform partial derivative for all the variables involved, okay, for function u for the first function, and the second function v will be partially differentiate in the second row. Okay, so the formula will be del u del x del u del y. Okay, because you just involved with two variables, which are x and y. Okay, same goes to v here. You will differentiate your v with respect to the first variable and then del v with the second variable. Okay, so this is the idea. And then you later on, okay, after you partially differentiate them, you will find determinant by using determinant of matrix 2 by 2, because here you have two rows to score two columns, so you'll be dealing with 2 by 2 matrix. Okay, so do you still remember on how to find the determinant for 2 by 2 matrix? Do you? Okay, so it is easy. It is just multiplication of these two, okay, cross product these two minus with cross product of this, okay, minus. That is the determinant for 2 by 2, okay, or in this case we are finding the Jacobian. Okay, so the name is Jacobian. Let us proceed to find the partial derivative of our function. Okay, so del u del x, look at u here and concentrate on x only, treat dy as a constant, so you will get exponent negative 2x, differentiate negative 2x, you will get negative 2, so sine 2y will be your constant. So just remain the position of sine 2y because it is the multiplication. Alright, it's done for first variable. Proceed to the second variable. So look at y. Okay, concentrate on y. Treat your x as a constant. So you will get exponent negative 2x will remain. Okay, differentiate sine 2y. That will give you cos 2y. Differentiate 2y. You will get 2. Okay. So done for the first function. And proceed to the second function, which is our v. Okay, so differentiate v here, look at the x, so you will get exponent 2x, differentiate 2x, you will get 2, and then cos will remain. Okay, so done for the first variable. Proceed to the second variable here, which is for y. Concentrate on y, differentiate y, so you get exponent 2x, cos, differentiate cos, you will get negative sign, so sine 2y, differentiate 2y, you get 2, so that will give you negative 2 because negative cos differentiate, you get negative sign. Alright, and then cross product this to find the determinant. Okay, so cross product this, you will get negative 2 times negative 2, that will give you 4. For your exponent, you need to use the property where the multiplication of two exponent, the power will become addition. So negative 2x will plus with 2x. Okay, check the property of exponent. Multiplication or division of exponent, you will get this. Alright, so y for sine, sine 2y multiply with sine 2y, that will double the power of sine and the angle will remain 2y. Okay, so multiplication of two same trigonometry does not double the angle, but it will double the power of the trigo. Okay, so sine 2y, not sine 2y for y squared. That is wrong. Okay. Okay. Once you're done with that, don't forget it is always minus. So put minus. And do for the second cross product of this. Okay, so that will give you 4 exponent of negative 2x plus 2x cos 2y times cos 2y, you will get cos squared 2y. Okay, and then simplify whatever you can, you will get 4 times 1 because this, okay, we reduce to exponent power 0. Okay, exponent power 0 is equal to 1. Alright, this is sine squared 2y. Same goes to that, you will get 4 times 1 cos squared 2y. So, you factor the 4 out, you will get sine 2y minus cos squared 2y. Okay, so this is the answer, or you can simplify this to 4. The property of this, if I'm not mistaken, that is equivalent to cos 4y. Okay, you need to check on that. Okay, so cos 4y. Okay, because this part, if I'm not mistaken, okay, please check on this. Okay, this will be equal to cos and then you need to plus the angle A plus B. So the angle here is cos 2y plus 2y. So that is cos 4y. Okay, so that's why you got cos 4y here. Okay, refer to trigo identity. Can you please check on this? Okay. Because the symbol here is minus. If plus, it is. Because plus, you have a property where cos theta plus sine square theta is equivalent to 1. Okay. Since the angle, the operation here is minus, so there is a one property for this trigonometry where sine square, the the property is like this. Sine A sine B minus with cos A cos B is equivalent to cos A plus B. So since our A and B here has same angle here, so that will give you sine AB, sine square AB minus cos squared AB here. Yeah, where our AB here is 2y. Okay, so check on this. Right, so the answer is 4 cos 4y. If you don't remember this in the exam, okay, you do not remember the trigonometry, it's fine. Just leave your answer in this stage. Okay, just in this step. Okay, just until there. Okay, until there. That's fine, no worries. Okay, so this is the example of the function where you just only have two functions, u and v. Alright, so since you have two functions with two independent variable x and y, you get a Jacobian or determinant for 2 by 2. So if you have 3 and more, so your system will increase. Okay, you have more functions, so the metric will increase. The order of the metric will increase. Alright, so you need to find the determinant by using the method that we have learned in chapter matrices. Okay, so this is 2 by 2. If 3 by 3 matrix, then you need to apply whatever method that we have learned. Okay, that we have learned. We have inverse method, we have adding the two column and so on. Okay, go back and check. Alright, so in this solution, okay, I use the row, the column as for my first function and the second column for my v. Okay, my second function. So I will treat my variable x in column and my variable y in the second row. Okay, sorry. X, my first variable in the first row and my second variable in the second row. So it will be different. Just now, what I did in the previous solution, I treat my first row for my first function and this second row as my second function. Okay, while for the column, I treat this for my first variable, I treat the second column as my y for to partially differentiate my second variable. Okay, but in this solution, okay, the solution given here, you find the Jacobian by alternative arrangement. Okay, but still you should get the same answer. See here, the second last solution, you got the same determinant, same Jacobian. Okay, so negative here is no negative. Alright, so same answer regardless of which formula for the Jacobian you use. Alright. Okay, so what is the use of Jacobian? Jacobian can be used to find the inverse function for partial derivative. Okay, so let's say you have function u and v, okay, which is depending on two independent variable x and y. So your u is a function that is depending on x and y, while v is also a function that is depending on the same variable x and y as well. Alright, so if you want to find the partial derivative with for your function, where you need your del x del u, okay, you need del x del u, del y del u, del x del v, and del y del v. Okay, you can use the formula given here. Okay, so to find del x del u, that is equivalent to del v del y over the Jacobian. To find the del y over del u is equivalent to negative of del v del x over the Jacobian and so on. So even though you can refer to the formula in your exam, okay, but I still want to explain on how you generate this formula. Okay, this is counted as a inverse function because you have function u here which is depending on x and y. So if by right, if you differentiate your u partially with x, you should get del u del x. Okay, so if you want to find the inverse function of your partial derivative here, okay, you cannot directly inverse this by using 1 over del u del x, thus you get del x del u. Okay, you cannot do this way for partial derivative, okay, with a different function depending on the variables. Okay, what you need to do is you need to use the Jacobian method. So del u del x is not simply inverse, okay, invertible to be like this, but del u del x is this. Okay, is equivalent to del v del y over the Jacobian. Okay, same goes to del u del y. You cannot just simply invert this to be del y del u. Okay, del y del u like that, which is equivalent to 1 over this. But you need to apply Jacobian where it is equivalent to negative of del v del x over the Jacobian and so on. Okay, so in the next slide, I will teach you on how to come out with this formula. Okay, right. So we know to find the Jacobian for two functions that is depending on two variables. Okay, you will get 2 by 2 determinant. Okay, 2 by 2 matrix. Sorry. Okay, so how do we formulate or we come out with this formula from this Jacobian? Okay, so how? Okay, let us start with this Jacobian. Right, so from here we know that Jacobian is finding the determinant of this, so we cross product that minus with cross product of that. So let us do that. So this is del u del x multiply with del v del y minus with this del v del x times with del u del y. Okay, alright. Okay, if you want to find the del x del u, so here this one is what you have del x. This is del u del x, right? So treat this as del u del x times del v del y equal to Jacobian. So you get one formula where del u del x is equivalent to, sorry, okay, I will write this again. Okay, so you have Jacobian equal to del u del x del v del y, and you can ignore this part because you just want to find the for del u del x. Okay, so here you will swap the position here. Okay, del u del x, you take it to the left hand side, that will become del x del u, and to this j, take it to the right hand side so that it will become del y over the Jacobian. Okay, right, so from the same formula here we can do for del y del u. So where is del y del u? Del y del u here. So we will consider this, all this part. Okay, so Jacobian is equivalent to negative del v del x del u del y. So take del u del y to the left hand side, that will become del y del u, and that will left you del v del x over the Jacobian. Okay, so same here, same here. Okay, now for del x del v, where can you get del x over del v? Del x del v is here. Okay, so you can take this to the right hand side. So you will get j equal to negative del v del x del u del y. So because you need del x del v, which is this, take this to the left hand side. So you will get del x del v, and you left negative del u del y over the Jacobian on your right hand side. Okay, so similar, isn't it? Okay, same goes to this one. Where you can get del y del v, you can get this from here, del v del y. So g is equal to del u del x multiply with del v del y. Okay, you take del v del y to that side, that will give you del y del v equal to del u del x over the Jacobian. So similar. Okay, that is how they get the formula, right? Okay, so Jacobian is the determinant. Okay, this cannot be equal to 0, right? When we want to consider formulation of this, and this, we will treat this. We need to treat one of these two parts, okay, to become equal to 0. Okay, so since this Jacobian cannot be equal to 0, between this, the first and the second term here, okay, the second term here cannot be equal to 0. Thus, this one should be equal to 0. Okay, in order to find for del x del u, this term, okay, the first term must equal to 0. Okay, and the second term cannot be equal to 0. That's why we ignore this. This cannot be equal to 0, so we ignore this in order to find for del x del u, because this part on this should be equal to 0. Okay, same, and this will apply to other formula as well. Okay, when we want to find or formulate the formula for that particular partial derivative, we need to equate that equal to 0, and the other term shouldn't be equal to 0, because the condition for Jacobian or the determinant, it cannot be equal to 0. Okay, simply say it is like this. If I have equation m which is equal to a plus b, and the condition said m cannot be equal to 0. Okay, so since m cannot be equal to 0, if I do a plus b, okay, and the condition must not be 0, okay, so these two unknown a and b, they cannot be equal to 0, because if a 0 b 0, you will get the equation 0 plus 0 equal to 0, but the condition say m, which is a plus b, cannot be equal to 0. Okay, so in order to make sure it is not equal to 0, okay, if we want to satisfy the condition, we have other choices where a equal to 0, and thus your b cannot be equal to 0. So b can be any number, 1, 2, 3, 4, 5. Okay, if you do this, it still satisfy the condition. Or a cannot be equal to 0, but b can be equal to 0. Okay, so this is what we did to our Jacobian part. In order to solve the equation, one of the unknown here, one of the term, whether a or b, should be equal to 0 in order to solve. Okay, same to the Jacobian one. Since we want to solve for del x del u here, so the first term, we need to solve for the first term. So the first term must be equal to 0 in order to solve this. Okay, in order to find del x del u. So this part should be 0. Okay, sorry for what I have said. Okay, so this part should be 0. Okay, so the second term should be 0. This should be 0, so that this one should not be 0 in order to solve for the Jacobian. Okay, this is simply what we did to the Jacobian one. One of the terms should equal to 0 and the other one cannot be equal to 0 in order to solve the solution. Right? Okay, so let us proceed to the next example to find for the inverse of the partial derivative. Alright, so we have the same function as we did in the first few slides just now. Okay, you have u and v, okay, with this function. So do you still remember that we have find the Jacobian for this function to be equal to 4 cos 4y. Okay, so remember this. Alright, so now you need to find the inverse of this partial derivative. Then you need to apply the formula of Jacobian inverse partial derivative, okay, by using the Jacobian. Okay, please take note that we have found the Jacobian for these two functions. Okay, the first and second function here, where the Jacobian is equal to 4 cos 4y. Okay, now we will apply the second second step. Okay, apply the formula of finding del x del u, del y del u, del x del v, and del y del v. Okay, so your task now is to find the partial derivative of each of these functions with respect to x, with respect to y. This one del v del x, and find del v del y, and then apply into formula to find del x del u. You need del v del y over the Jacobian. So apply into the formula, you should get this. Alright, so same goes to this. To find del y del u, you need negative of del v del x. You need negative of this one over with the Jacobian just now, which is 4 cos 4y. Okay, so you simplify, you will get this and continue. Okay. Okay, for the next example, it will be a little bit complicated. Okay, become more complicated because you will be dealing with 3 functions. Okay, so 3 functions. The first one is z. Oops, why kuning? Okay, sorry. Okay, so you have 1, 2, 3. But the thing now is you need to find and each of these functions you you have 2 independent variables which are x and y. Okay, x and y. Same goes to in u. You have 2 independent variables x and y also for your v. Okay, so here you need to find del z del u. Okay, so just concentrate on this one. You find del z with respect to this and this. Okay, so this one same goes to this one, del z over del v, del u del v. So what you need to do is you need to apply the chain rule. And this one, if you compare with the previous example in part 2 or part 3, if I'm not mistaken, it looks similar. But if you look at that, function u, function x, you have 3 functions as well, but your second and third function is a function of x. It's not function of u as written in here. Okay, the previous one, you have function z in term of u. In term of x and in terms of y. Y, x and y is in term of u and v. Okay, y is in term of u and v. Okay, but in this Jacobian, right, you have z in a function of x and y, while your second and third function is independent variable, independent function of u, which is also in the same variable x and y. Okay, so they are different, so you cannot apply the same method on finding this when you're dealing with three functions here that are having two independent variable x and y. You need to use Jacobian method. Alright, so for this one, it will be a little bit longer. The step will be a little bit longer because you need to apply the chain rule in order to find your del z and del u, where del z del u is equivalent to del z del x multiplied with del x del u plus del z del y multiplied with del y del u. So you will get del z del u. For del z del v, you should do partial derivative with respect to x and x with respect to v plus with del z with del y del v. So you will be having or dealing with two chains rule in order to find for the respective question. Okay, so we do one by one. Here, once you formulated the chain rule here, please take note that in order to find for these, and these, you need Jacobian. Okay, you see, you need to calculate your Jacobian, and then second step you find for del x del u, and then you can apply the chain rule. Right, so it is a long step. So I have written down these two chain rules in the first slide just now. Right, then we proceed to the next step. Okay, for each of the function z, u, and v, you should find their respective partial derivative with respect to x, partial derivative with respect to y. So you have x and y. So partially differentiate each of them with respect to x and del u del y, because in u as well you have x and y. Same goes to v, partially differentiate del v with respect to x because you have variable x here, and partially differentiate your v with respect to y because you have variable y in v as well. Right, so these are their respective partial derivative with respect to the variables. Alright, once you have found this, then you need to proceed to the next step where you need to find for the Jacobian. Okay, in order to find the Jacobian, it will just involve with u and v only. So here, treat the first column for your first u and the second is for v, while each of the row you do for respective variable x and the second row for your y. Okay, so just involve with u and v here for the Jacobian. Alright, because here what you need is just del x del u, del x del v, del y del u, del y and del v. There's no need to find for del z. So that's why the Jacobian only involved with two functions. Okay, so found, apply the same, use and apply the same procedures, the method as I shown in the previous slide. So you got your Jacobian to be this. Okay, and then apply the Jacobian into the formula of finding all these four partial derivative. Okay, right, and then you can apply, okay, you can substitute all the partial derivative involved, okay, into the first chain rule and the second chain rule. Thus, this is the answer for your question. Okay, alright, so done. It will be a little bit longer lah. Alright, but don't worry, just follow the step. Okay, so that's it for the fourth lecture, and we have one more part to go. Okay, this is the fourth part, the part 4 lecture. You have only one more part left, which is part 5. So that will end the chapter 5. Okay, the chapter 5, and thus end the course EQT 101. Okay, I'll see you shortly in part 5. Okay, you can start doing your tutorial, and if you have any difficulties to understand this, don't hesitate to ask. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.